The next aspect of this part is interpreting the slope and y-intercept for a least squares regression equation. Those numbers mean something, like anything in statistics. All those values, a number means something. So we'll use an example to explain it, but here's the language that we're thinking about, right? The slope represents the rate of change, how much the y changes for every x. And again, that depended on the context. So are we talking about the size of a house and the price of a house, how much it sells for? So the price, right, increases when the size increases. By how much, right? And that's what the slope would tell us. The y-intercept represents the initial or starting value. What's the y value when the x value equals 0? What would it be? Sometimes the y value doesn't make any sense in the context of the problem, right? And that's what it's explaining right here. Um, but again, we're going to use these equations to make predictions or get estimates for a y value. So something to keep in mind. Again, that's given we have a correlation. So back to this one here, let's consider again the equation that predicts a person's height. Sorry, their weight, right? When we know their height, it's a little bit typo there. Um, this is the least squares regression. The slope is 1.09 or 1.1. We're going to round off. 100, negative 110 is the y-intercept, and there's the interpretation. In this y-intercept case, it doesn't make sense that when someone's height is 0, their weight would be negative 110. It doesn't make sense. Our equation really is only good estimate for data that is within the. You can make predictions for data that are, or for values that are close to the data. So that's something to keep in mind. We'll have to look at that a little bit more. And in the slope is 1.1, which means for every 1 inch increase in height, 1.1 about, we predict, sorry, for every 1 inch in height, we predict, right, because the weight is the y value, we predict 1.1 pound increase. So if someone gets taller, we increase their weight by 1.1. They're just average values, okay? These are average values. Let's go take a look at the ARTISTAT a little bit. So in the ARTISTAT right here, we're going to look at linear regression. You'll click on that, and then we'll get into this here. And you have all, again, different data sets. We'll end up entering our own data set, but for now, let's just look at one that exists. This is the price of a house and the size of it. So those are the values you can see. And we have data for 100 different homes. So you could see, looks like a positive correlation. Now you have to choose here a regression line, and so then the regression comes, and then you get the equation right here. Y hat equals, so this is the equation we use to make a prediction. And what does this data mean? Again, 77 is the slope, and you can see that down here. The intercept, the y-intercept is 9,161. In this case, the slope means that the price increases $77 for every 1 unit rate. This is for every 1 square foot increase, the price increases by $77. So you can imagine if you have a 100 square foot increase, you can then estimate the increase in the house. That's again on average based off of the distribution of the two quantitative variables. R value, that's really strong. We talk a little bit about the correlation of determination. That's for more advanced classes, but again, this represents 58% of our data can be explained by these two variables, something to think about. Again, I know it's not as intuitive, but again, there's a strong relationship between size and weight. You can also find predicted values. You click here, and if we wanted to make a prediction, so if you bought a 2,000 square foot house, you type in 2,000, you would predict that it's 163,000 you're estimating, okay? There's also residuals and stuff, which we talk about in the next lesson. How far off is the actual data compared to our estimates? That's what the residuals are. So we can see here again, I just want to end on here. We come back here. Hopefully you can read this and that makes some sense to what I was saying. Here, note the y-intercept interpretation may not make sense, and that's okay because our prediction really is only good for values within the data set or very close to our data sets. We can't really use making predictions when they're really far away from the data that we have. So again, on that example of height and weight, like we haven't seen the data, but um, if we think about the one about size of house and price, if I had a 20,000 square foot house, I wouldn't use that to make a prediction because on the data I only went up to 4,000, and so 20,000 I wouldn't be so confident with the estimate because it's so far away from my data.